Okay, thank you. Thank the organizers for organizing this wonderful meeting and giving me an opportunity to talk about something which I've been thinking about over the past few years. So I'm going to deal with, is there a way of getting rid of that thing? Yeah. Okay, I'm gonna use it. Yeah. So I'm going to talk about gauge invariant notions of entanglement of color degrees of freedom. And much of our motivations actually come from holography, but I think this has a much more general applicability and something I would like to learn in this workshop as well. Now, in area CFT, a quantum field theory in some number of space-time dimensions is dual to a theory which contains gravity, typically a string theory or M theory in higher dimensions. And one of the lessons we have learned over the past couple of decades is that there is a deep connection between entanglement of states and emergence of a smooth bulk description. In a simple word, what this means is that more entanglement means more of the bulk can be constructed. There are, of course, much more quantitative ways of staging this, but I think this will be good for our purpose. Oh.
I think you should be working now. Yeah.
Okay. Oh, I see. Okay.
Yeah.
Huh? Okay, good. When I say that, the kind of entanglement which one usually talks about are entanglements of degrees of freedom, which is in some sub-region on the base space on which the field theory is defined. So you have the field theory defined on some space. There is a small region of that space, and you want to talk about the entanglement of degrees of freedom which are inside versus the complement. However, there are versions of holography which sometimes predate the ADS-CFT correspondence, where the gauge theory dual to the bulk gravitational theory has no space to begin with. These are typically gauged quantum mechanics of matrices. Some well-known example is something called the C=1 matrix model. It's a quantum mechanics of a single Hermitian matrix, and in an appropriate limit, its dual description is two-dimensional string theory. Another well-known example is the BFSS matrix model. It's a quantum mechanics of 9 Hermitian matrices and their supersymmetric partners. This is believed to be dual to 10-dimensional string theory or 11-dimensional M theory in suitable regimes. There are several other examples, that the BMN matrix model is another example. And what we would like to understand is whether this slogan that entanglement creates space, whatever that means, is valid in those cases as well.
How about twisted image Hawaii?
Yes, image Hawaii, yes, of course, yeah. Well, it's sort of intimately related to BFSS and IKKT in a way, particularly the IKKT. Now, even for standard ADS-CFT, we typically never get an ADS space by itself, but it comes together with an internal space. I mean, the classic example being ADS5 cross S5. Base space entanglement is related to the emergence of the radial direction of ADS space. And it's a natural question to ask, is there some kind of entanglement which is responsible for generating a smooth S5? Because from the bulk point of view, S5 is as good as a space compared to the ADS part. As we will see, to answer this question, which I don't have an answer to, but we're trying to set up the framework, we need to think about notions of entanglement of the matrix degrees of freedom, or in more general, of internal degrees of freedom. As an aside, I should point out this question is also related to what is called the sub-ADS scale locality. Normally, one might think that the space-time which you generated is local at the scale of the curvature of the space-time. But in all these examples, we do know that it is local to a much smaller scale, typically like the string scale. And as I mentioned, regardless of holography, the concepts which we will develop should be useful in many interesting situations in many body physics, some of which I'll mention. So let's begin of how to think about such a quantity. So I'll have in mind in general quantum mechanics of some number of Hermitian matrices, which I'll denote by Mi, ions from whatever number of matrices you have. And these are n by n matrices, and I'll work in the large n limits. It's gauge quantum mechanics. So in the action, there is a gauge field. But of course, it's a gauge field in 0 plus 1 dimensions. So it has no dynamics except that it produces a Gauss law. So the normal way of treating the problem is to choose a gauge. For example, AT equal to 0. So gauge away the gauge field. We are thinking of real time. So you can do that. And then as a result, you get a Gauss law condition on the states, which basically tells you that there should be a sum over I here, the total UN, remaining UN gauge transformation, and it keeps the physical states invariant. And this is the generator of those rotations. Naively, you could think that, well, I have an n by n matrix. So why don't I just pick some number of those matrices? These are the degrees of freedom, and think about the entanglement of, for example, in this case, these 4 such matrix elements with the rest. However, this is of course not gauge invariant, because the remaining gauge symmetry, which is the constant UN rotations, are going to scramble up all the matrices, and there is no invariant way you can think of just taking a sub-matrix. Things are a little bit better if you have something like the Coulomb branch, where the symmetry naturally breaks into smaller groups, and you can think of one unbroken group with another. But in general, this is difficult to make sense of. So we want to think about this in a completely gauge invariant way. And the way we would like to think about this is the following. Given some number of such matrices, consider a Hermitian combination of those matrices. And I'll give an example of this. So F of Mi is a matrix value operator, which itself is a Hermitian operator. And now we construct a projection operator, which is defined according to this. And as you can see, what this projection operator does, it checks for eigenvalues of this Hermitian operator and restricts the eigenvalue to a certain interval A of the real line. Being a Hermitian operator, the eigenvalues are real. So I can ask whether the eigenvalues lie in some real line. This being a projector, I can start with any general gauge invariant operator, some products of the matrices and the canonically conjugate momenta, ordered in some particular way. And to each of these factors of the matrix or the conjugate momenta, I project them out using this projector. As a result, I get a subalgebra of operators, which I can write it in this following way. The trace makes it gauge invariant. To look at the meaning of this, as I said, the projector projects onto a subspace in which the eigenvalues of the Hermitian matrix lie in some interval. For example, I look for eigenvalues which are all positive. The meaning of this becomes clear if we pick a gauge where this single Hermitian combination of the matrices is itself diagonal. For example, that combination of matrices may be just one of the matrices, M1. So we are going to a gauge in which M1 is diagonal and all the other matrices are whatever they become. So clearly the projection of the type we are talking about takes this matrix and removes everything. All this M1 now has become a diagonal matrix in this gauge, and this projection puts everything to zero except the ones, for example, which are positive, which is the condition that this combination is positive. The result of this is that the original Hilbert space now breaks up into sectors. Given the matrix, there is a certain probability that certain number of these eigenvalues satisfy the condition. So a sector is characterized by the number of eigenvalues k, which are in this case positive. For all the other matrices Mj, which are not diagonal anymore, this kind of projection retains a k by k block. And there is a density matrix, a reduced density matrix, which evaluates all the expectation values of this projected subalgebra operator. Because of its structure, that reduced density matrix is sector-wise block diagonal. So rho is like this is like rho 1 is the reduced density matrix in the sector where there is one eigenvalue in that region of interest. Rho 2 has two eigenvalues in the region of interest, and so on. The k sector, rho k, is an operator in a smaller Hilbert space. And that smaller Hilbert space is, in this case, the quantum mechanics of a k by k matrix. A little more explicitly, in this gauge, if we can divide the matrix elements into parts which belong to the ones which I keep and the ones which I don't want to keep, and the matrix elements of the reduced density matrix is obtained up to a combinatoric factor by integrating, by tracing over the degrees of freedom which we do not keep. It is important to note that there is a sum over sectors because the Hilbert space is not a direct product, but a sum of direct products. So as a result, each of these rho k's in each such sector is not normalized. In fact, the trace of that is simply the probability to find k eigenvalues in my region of interest. The entire density matrix, which is sum over all such sectors, the direct sum, is of course normalized. And therefore, one can assign a von Neumann entropy with that object. So this is that von Neumann entropy. I don't know why there are two equality signs. And if you can write that simply as trace rho k log rho k, but you can also introduce a normalized density matrix in each sector to write it in this rather a slightly more clearer form, where there is a part which is just a classical part. It's just a kind of a Shannon entropy, which reflects the fact that there is a certain probability for the eigenvalues to be in that range. And then there is a quantum part, which really measures the quantum entanglement of the matrices. The sum over sectors is crucial because this just follows from the gauge invariant of that notion. So as a result, even though in each such sector it does appear in this particular case to be a sort of subset of the matrix elements, that itself doesn't provide a gauge invariant notion. It's only when you sum that you get a gauge invariant notion. When applied, for example, so why do we think of a thing like this? So let us apply this to one such model, which is the BFSS matrix model. This has, as I said, 9 matrices which have their fermionic partners, and I'm not going to talk about the fermions. In this model, in a low energy state, each matrix corresponds to a coordinate xmi corresponds to a coordinate in a 9-dimensional emergent space. And this emergent space becomes the space of the 9 plus 1 dimensional string theory, or in some other limit, 10 plus 1 dimensional M theory. In fact, in low energy states, the eigenvalues of these matrices M are locations of n d0 branes, while the off-diagonal elements are open strings, we join them. What this means is that the projector, which restricts the eigenvalues to a single matrix F of M to lie in a certain region, then leads to a restriction in the target space specified by that same function as a function of the coordinates up to some ordering ambiguities. So we are really measuring what I'll call target space entanglement, namely the entanglement associated with a region in which the D0 branes move. For example, if I once again giving an example where this function is just one of the matrices, you can represent these D0 branes, which are roughly the positions of the eigenvalues of the diagonal elements like this. And if I have a condition that this is positive, these three are the 3D branes of interest, and the others are to be integrated over. And then you have to sum over all possible sectors. If I was going to use a function which is like the sum of m square minus some number, the region in the target space which encloses these D branes of interest is a spherical region. And typically this is like the kind of pictures which you draw with open strings joining these D branes. And the question is, which ones are you keep and which ones you are going to integrate over. So what this means is that what we have defined, therefore, is a notion of an entanglement with a region of space in a gravitational theory. Now that's a little bit weird because there is no diffeomorphism way of defining a region in a theory with dynamical gravity. However, our definition is not in the gravitational theory. Our definition is in the dual theory, which is regular quantum mechanics. So that's a precise quantity which in a certain limit becomes associated with a region of space. I should mention, but not elaborate on, the fact that the Gauss law actually has an effect in this calculation, because even though these matrices might appear to be independent, they're really not so independent. They are related by this Gauss law condition, which actually plays a key role in the entanglement. Definitely skip on that. This can be extended to gauge field theories in some trivial ways, but also in some non-trivial ways. But let me give you some examples. The simplest example is single matrix quantum mechanics. Now, as is well known, a single matrix quantum mechanics, since it's a single matrix in the AT equal to 0 gauge, you can diagonalize this matrix. And so it's a theory of these eigenvalues. And for a well-known change of variables between the matrices and the eigenvalues represent locations of n fermions, which are moving in an external potential. It's now possible to show that the notion of target space entanglement, which I developed, is exactly the notion of a usual base space entanglement in second quantization. If you just have a system of n particles, you can write it as a second quantized theory, and there is a usual notion of entanglement in space of that second quantized theory, and this is exactly the same. In quite generically, you can actually calculate this object, and here is an answer for a small region in a slowly varying potential in some kind of WKB approximation. It goes as 1/3 log of the interval size multiplied by what I call the local Fermi depth. The factor of 1/3 and the logarithm reflects the fact that the low energy excitations of the Fermi surface is described by a massless scalar in 1+1 dimensions with a relativistic dispersion relation, because we are talking of small fluctuations of the Fermi surface. In fact, the effective theory of such oscillations is given by a bosonic theory of this particular form with a coupling which depends on the location. And if this coupling was not there, this would be just like a relativistic 1+1 dimensional boson whose entanglement entropy is 1/3 log of the interval in units of the UV cutoff. Here, instead of having the UV cutoff, you get a finite answer with the local Fermi depth playing the role of the UV cutoff. From the point of view of the, now I should also emphasize that this cutoff is, from the point of view of this theory, is a non-perturbative effect because it appears inside the log. In fact, there are some simple examples where you can work this out perturbatively in the coupling. And what you find is that to every order of perturbation theory, the answer is divergent, but you can sum the perturbation theory and then exact answer reflects the finite answer which you get from the fermionic theory. This is interesting from the point of view of holography because, as I mentioned, this theory is dual to two-dimensional string theory, where the fermions are d-branes. The bosonic collective theory is related to the single dynamical closed string mode. The coupling is the string coupling. And the finiteness of the entanglement entropy, which has its origins in the fact that n is finite, but remains finite in the particular limit in which it actually becomes a string theory. And as I emphasize, this finiteness of the entanglement entropy is non-perturbative, and it's related in the big picture to the finiteness of the Newton constant. Since time is short, I'll give you another example from multiple matrices where the coupling enters. And this is largely a calculation by Frenkel and Sean Hartnell. This is what is called a mini BMN model, where instead of having all the 9 matrices, you just have 3 of them. And the potential is such a form that the ground state solutions are fuzzy spheres, namely the matrices are proportional to SU2 generators in some representation. You can use this definition in order to calculate the entanglement which is associated with, for example, a capped region of this fuzzy sphere. What it amounts to is, in fact, in a particular sector, retaining an m by n block of that n by n matrices. And after an interesting calculation, what you find is that, that's my thing, okay. After an interesting calculation, what you find once again that the coupling constant of the theory on the fuzzy sphere makes its appearance. I believe for this kind of quantity, this is probably a very generic feature. The finiteness of the entanglement entropy is a coupling related fact, and in fact, it is strongly reminiscent of the Bekenstein-Hawking formula, where once again the Newton constant plays that role. And I think I am out of time, so I'll just quickly mention some applications to things beyond holography. One of the applications would be the following. Now, when you have a many-body system, which you can write in terms of a second quantized theory, then people have developed techniques of calculating the entanglement entropy in second quantization. But sometimes in many-body systems, you can have good wave functions, but the second quantized description is complicated because of strong coupling. The classic example being the Laplacian wave function. The way we have set up the problem and the way we showed that our definition is equivalent to a second quantized definition, then tells you that you can use just the wave functions to obtain a result for the entanglement associated with the region of target space. And we're sort of following up on some sort of toy models like the Calogero-Sutherland model, which is kind of a model of anionic wave functions to understand this. The second thing I would like to mention is that there's also a connection of how this entropy behaves in phase transitions. And there's a well-known connection. This is probably my last slide. Okay. There's a well-known connection between entanglement entropies of usual base space and with phase transitions. For example, the confinement transition. It turns out, and I think again it's quite general, that at least for large N phase transitions, this object does act as some kind of order parameter. And this is not very hard to see. For example, 2+ 1-dimensional pure Young-Mills theory, which reduces to unitary matrix model. Another avenue which we are exploring is to develop some tensor network methods, so some Mera-style methods, which very importantly depend on entanglement structure of the ground state wave function you're trying to calculate. And of course, for theories where you don't have any base space to begin with, think about what kind of entanglement you're going to create. And so that, I think, would be a good complement to recent bootstrap methods for multi-matrix models. Thank you. That's
Time for a couple of questions.
How do you expect this entanglement to grow with the number of matrices that you said if you're going to apply methods?
right. So we would expect to grow as n squared. It's a very rough counting because, in the sum over sector, the sector which has roughly, equal order n divisions is dominating due to combinatorial factors. There is some evidence for that. Particularly, I think Albion Lawrence and collaborators have done a kind of a Born-Oppenheimer calculation of 3 or 4 matrices, and it seems to be consistent with that expectation, but I don't think the answer is really no. Yeah,
You mentioned that this phase transition and the one blockade model is related to entanglement.
So what happens? So yeah, so this is 2 + 1 Young-Mills series, so one packet. So it's a unitary matrix quantum mechanics. So but as you know, in the unitary matrix quantum mechanics, potential is like this, a periodic potential. And the phase transition happens with the Fermi level constant at the top. So if you take so now we're talking of the space of eigenvalues, which is this target.
So you're not talking about growth.
No, this is quantum
That's
mechanics.
what I was asking.
Yeah.
about.
So it is light cross-fitted earlier because the cut of the eigenvalue distribution changes, but not for.